Well, what a terrific day today. What an incredible day. Good morning. For those of you watching from outside MIT, I'm Rafael Reif, and I'm the president of MIT. Look, I know we all want to hear from the LIGO experts, and that includes me. But I would like to be brief and just make 3 points. First, to the entire LIGO team at MIT and Caltech and around the world, my heartiest congratulations. We truly stand in awe of the creativity and rigor of the LIGO experiment, a truly scientific triumph. And we're equally inspired by your decades of ingenuity, optimism, and perseverance. The instigator of the LIGO project and its leader on the MIT side is Professor Emeritus Ray Wise, who, as you know he happens to be in DC right now, and he is also an MIT graduate. Even though Ray is in Washington, I'm delighted that we have with us here Rebecca, his wife. And Rebecca, I'm certain that this project turned into your life's work too. So we congratulate you as well. A second point for the MIT community. You often hear me refer to MIT's mission statement. You often hear me say things like it directs us to advance knowledge and to educate students and to work with others to bring knowledge to bear on the world's great challenges for the betterment of humankind. So consider this. The LIGO team has advanced knowledge by uncovering fresh news about the building blocks of the universe. And they have opened a whole new field of inquiry, so knowledge will keep on advancing. What's more, the experiment at the heart of LIGO actually began as a way to educate students, a thought experiment that Ray Wise designed to get his students thinking. Since then, LIGO has been a proving ground for 3 generations of MIT students, 2 of them now on our faculty. And LIGO's global team came to include hundreds of researchers across multiple institutions. It is hard to imagine a more beautiful expression of the ideal of working with others on a great challenge for all of humankind. In short, for MIT, today's announcement is both a great achievement, but also a great example of our aspirations. My third and last observation is broader, and is addressed to those who are outside the domain of scientific research. At a place like MIT or Caltech or the NSF, the value and power of fundamental scientific research feels obvious, not just today, but every day. Basic science is a source of wonder and a wellspring of innovation. It is the currency of human progress, and our modern life, a modern way of life, would not exist without it. Without basic science, our best guess never gets any better. Without basic science, innovation amounts to tinkering around the edges. And when basic science advances, society advances too. As today's announcement makes clear, basic science can be electrifying, revolutionary, and catalytic. But the LIGO project demonstrates another truth about fundamental breakthroughs, that the work they require is painstaking, rigorous, and slow. And that means something else very important. It means that if as a nation we want the results of basic research, if we want the great discoveries, the new technologies, the cures, the inventions, the wealth, if we want all that as a nation, then we have to pay for it as a nation. The United States has a time-tested way to make those sustained investments. The system was invented in response to the terrible challenges of World War II. President Roosevelt sought guidance from some outstanding scientific advisors. This room, in fact, is named for one of them, Vannevar Bush, former Dean of Engineering, right here at MIT. Together, Bush and others helped FDR develop and pursue a wartime strategy of advanced scientific research and development. Ultimately, that strategy produced the technologies that brought the war to an end. Federal support for basic research was a big, brilliant idea. By 1950, Congress and President Truman turned that idea into the National Science Foundation. And 30 years later, the NSF would send its first check to Ray Wise for the work that would lead to LIGO. Across the country, federal research investments reinvented American universities as powerhouses of modern scientific and technological research. In turn, the ideas that flowed out of academic labs helped deliver huge gains in productivity and employment by fueling one innovation wave after another. Today, the NSF funds about a quarter of federally supported basic research conducted by US colleges and universities, including almost 40 years of support for the work we celebrate today. The system the US uses to invest in basic research in partnership with the nation's research universities is a direct descendant of Vannevar Bush's big idea. Today is a wonderful reminder that investing in basic science is investing in our future. This distinctive American system for supporting great science is a vital source of our nation's strength. And it is something we should all be deeply proud of as Americans. That system belongs to all of us. And in that sense, today's discovery belongs to all of us too. Let me close with a personal note. On the MIT side, as we know, the leader of the LIGO project is Ray Wise. Ray has a webpage, and it contains this observation. Started in physics with a precept that only very important and finished work should be published. As a consequence, didn't publish much and got hell for it. Ray, we appreciate your high standards. And if you had to publish something, this one was an excellent choice. Now it's my pleasure to introduce another LIGO pioneer who was one of Ray Wise's star graduate students, the Marble Professor of Astrophysics and Associate Head of our Physics Department, Nergis Mavalvala. Nergis.
So hi, everybody. I'll just echo something we already heard. We did it. Yeah, we did it. We did it. Okay. So I'll just speak for myself very briefly. I've been doing this for 25 years, and this is perhaps the most exciting day of that 25-year journey. But of course, it's the greatest privilege any scientist can have throughout their career to be part of something that's truly game-changing, and I think we're here. This is a game-changing discovery. But science at this scale is not done, is not a small effort, and is not done by individuals. It's a very big group. So I would like to acknowledge our LIGO group here at MIT. We're here in full force. Will you please stand up, friends? Yeah. Now, I'll also remind everybody that efforts of this scale are not just done by scientists alone. It's also a great moment, a pleasure for me to share this moment with colleagues, friends, and of course, we have family members in the audience. I won't embarrass you by making you stand up, but maybe you can wave. Okay. So this is a day for all of us to share. I want to just reflect a little bit on what this discovery means. Why should we be so excited? You've heard it very many times. I'll just remind everybody. We've seen gravitational waves. LIGO works. Black holes exist. black holes collide, new black holes are born, general relativity works. Need I keep going? Okay? All right. So, so I now want to just say a few words about this detection, which, as we've heard many times, has opened a new door into astrophysics. And we're privileged to be walking through that door at this moment in time. And it's part of the testament of the process of discovery that humans engage in. So we seek answers to questions we don't even know how to ask. And this is something that's one of the most enduring and insatiable curiosities that humans have, is what's out there in the universe? What are we made of? Where did we come from? And this discovery is just a small step towards answering those questions, but with a completely new tool, gravitational waves. Discoveries like this are precisely what MIT does best. It's the perfect place to ask impossible questions and then make it possible to answer them. So I thank all my colleagues at MIT for having done this journey with us. LIGO was conceived here at MIT in the late 1960s and early 70s by Ray Weiss. Its success has been made possible by 3 generations of students and postdocs and engineers and staff members. MIT and Caltech partnered with the NSF to do LIGO when even the most optimistic scientist or even the most foolhardy scientist should not have done it. And yet we did. And Ray Weiss led that. Ray was actually a revolutionary in the classic MIT style. He actually believed, and he lives this every moment, which is that if you combine clever ideas with smart people, you'll get it done. And that he has done. He took a big gamble. We all took it with him, and it paid off today. Okay? It's a collective gamble. And I'll just say for myself, I was a graduate student in his lab in the 1990s. And, it was a heady time. LIGO had just been approved. It was going to get built. And I personally genuinely believed gravitational waves would be seen before I finished graduate school. I was wrong. And then I did what Ray did. I told my students they would detect gravitational waves before they were finished. And many are here to witness that, and some finished before. So, but it's been worth the wait. It's a big reminder to us that long-term investment in research really matters. If you want big discoveries, you have to do it in the slow, long way. So I want to acknowledge that we are here as a community here at MIT, and we're walking into a small piece of scientific history. When we look back at this time, 10 years, 20 years, 50 years, 400 years from now, MIT will have played a role in something that we hope is going to change the way we see the universe. So I also want to acknowledge our collaboration. This is a collaboration of over 1,000 people, and it's a remarkable thing, but this is a case where the numbers have actually added to the synergy rather than to the entropy of the system. And so I'm very proud to be part of that collaboration. Now, some of you haven't had the pleasure of going to visit the LIGO observatories, and I just want to put in a plug. You can have a pretty good virtual experience right here on campus. Come to our labs in Northwest Campus. They're really fun to visit, and we have some wonderful toys. Okay, so our room, the room is well filled with members of the LIGO laboratory. We have a lot of expertise in the room here. But I want to ask 2 of my colleagues to join me here. We're going to open it up just to questions. This is what you've been waiting for, to ask us all the difficult questions. So I'd like to invite Professor Matt Evans and Dr. Eric Katsavanidis to join me. Matt Evans is an assistant professor here at MIT, and Eric Katsavanidis is a senior research scientist and longtime colleague. And we are going to just let you ask us, at this point, more or less any question you want. We can't promise we can answer them all, but we will try. Thank you for being here. So.
Okay, I have a question. Do you have another observation in the can that you're going to share with us? And when do you hope to have another if you don't already have it?
I'll let Matt answer this one.
This is one of those questions that we anticipated. And I can say that we're here to talk about a really great discovery and one event in particular. There is data in the can, we're still analyzing it, and that's really all we can tell you about the data which is in the can. This discovery, on the other hand, I think will be sufficient to, let's say, brighten the day for today, and we can leave other things for other days.
Actually, we can say something a little bit more about it if we'll get slide number 7, please. So this is a figure from the paper that most of you, I'm sure, have already downloaded on your phones that just got released. And what you see there is that on the horizontal axis is the detection statistic. It's you can think of it as a signal-to-noise ratio, if you like. And on the vertical axis is the number of events that would meet that signal-to-noise ratio. The solid curves there are the background. That's the statistical noise in the detector. And the orange squares are events that we would name as events or foreground. And what you see is that the binary black hole we've all been talking about is on the far right of that picture. But then you also see that there are a couple of orange squares that are perhaps a little bit above the expected noise in the instrument. And that may also help answer your question, Eddie, of whether there were other events.
So if we pick the second most significant event there, the false alarm probability is a few %. And if we assume it's of astrophysical origin, then it would be another binary black hole system. But it's not of any comparable significance to the main event that we're talking about. So I don't want to downplay it too much. There's other things in the data that we've already looked at. But the significance of that event is much less than the one that we're talking about.
Nergis?
Do you have any?
No, actually, if since we are on this plot, might worth point out how we establish the significance of this event, namely the fact that you see it all the way out on that orange dots or squares, and then on the blue or black, you can see that we have not seen anything like that after simulating 200,000 years worth of that experiment. Mm-hmm. So this is something that we have expected with a probability of less than 10 to the minus 7 or something. And this is what sets the scale of the significance when presented in terms of Gaussian sigmas. And this is over 5 sigma significance.
Nergis, what was the primary technique used to improve from the original LIGO to the advanced LIGO? What did you do to exactly to improve it by a factor of 10?
Yeah, I'll give you a very simple answer, and then I'll let Matt show you a plot. So the simple answer is better everything. And then the more sophisticated answer comes from slide 12, please. We'll take that one.
Yeah, so I think better everything is a good way to sum it up. These interferometers have a sensitivity that's determined by the amount of laser power that we can get to circulate in the interferometer. And so we got bigger lasers. They also determined by how much ground vibration couples into the interferometer, so how much disturbance are we getting from the outside. So we got much better isolation systems involved. I think you saw a picture of the quadruple pendulum that Ray Weiss demonstrated. That was a single pendulum in initial LIGO. So we went from the thing that he was shaking in his hand to this much larger, more complicated object. So that gives us better isolation. And then the mirrors themselves are higher quality and much larger masses. So our test masses became better in essentially every possible way. And this combination is what took us from, you see a green-looking sensitivity curve on there? That was the best sensitivity we had with initial LIGO. Those plots are meant to show, as a function of frequency, what's the noise floor, the noise background in our detector. And if you compare the green one there to the red one just below it, that's the step from where we were last with the initial LIGO detectors to this first observing run with which we detected this event. The next step to the blue curve, you notice the blue one looks a little too perfect to be real. That's because that's where we're hoping to get to in the next few years with advanced LIGO as we finish a process called commissioning. And the light blue one below that is where I spend a fair fraction of my time, and that's thinking about how we go on from advanced LIGO.
Hi, Josh Sokol from New Scientist.
Where are you, Josh?
Oh, hi, Josh.
There you are.
You just turned on this machine and you detect a perfect, beautiful, high signal-to-noise event. What does that feel like? How exciting is that? How lucky is that?
We were really hoping that we weren't very, very lucky. So having the second event, which is of still marginal significance but present in the data, made us feel better. But we, in any case, feel very fortunate that such things, these large binary black hole systems, exist in the universe and coalesce at a rate that we were able to detect one after turning on initial LIGO or advanced LIGO.
But we also can't wipe the smile off our faces. Frank?
Can you say anything about the spin of these black holes?
Yes.
Can you say anything about the spin of these black holes, how fast they're spinning as well as their mass?
For the final black hole, we estimate the spin to be at the level of 0.6, 0.7. And there has been a detailed parameter estimation starting from the recorded signals in order to also limit or put constraints on the spin of the individual masses. But this is rather weakly constrained.
Maybe we can ask. Yeah, it's in the parameter estimation paper. I think one question that people might be asking is, are they nearly maximally spinning? I think we can say they're not nearly maximally spinning. So the spins are not close to the maximum possible.
And we don't see precession.
Right. Can I request slide 18 for so at the time that this paper came out a few minutes ago, these 12 companion papers also got posted, and so I encourage people also to, if you have specific questions on any one piece of it, these are not the titles of the paper. These are my two-word description of what the paper is about, and so there is a lot of details on some of the questions of the parameters of the source that we've seen. That's the top right. It's called estimating the parameters of the source. There is a paper on tests of general relativity that this source allowed us to do, and it's a kind of a remarkable achievement because it's the most relativistic system ever observed. And as a result, you can do tests of general relativity that are orders of magnitude better than the next closest thing that has been possible. So I'll just put in a plug-in for people who are looking for light reading tonight. So.
And tomorrow night and the next night.
Seth?
Hi, this is Robert Noya with Sky and Telescope. The gentleman before me basically asked my question about if you had constraints on the spins, but I wanted to follow up on that, and I did talk briefly with Matt about this before the press conference. If you have any constraints on the recoil velocity of the merged black hole.
No.
No. Since we can't measure the endocrine constraint, we cannot say much about the kick velocities.
Yeah.
So I'm curious, in your anticipated progression through the dark blue curve and the light to the light blue curve, how much of that enhancement comes from using quantum effects like injection of squeezed vacuum?
Yeah, so the dark blue curve, which is representative of the advanced LIGO design sensitivity, does not include any, we call it squeezing, is what we end up using. So that's using some quantum optics. There's none of that in the dark blue curve for the design of advanced LIGO. That's, I guess, because Nergis was still busy making that work when advanced LIGO was designed. And the light blue curve, which is representative of our anticipation of where we're going next, is something where we expect to be using squeeze states of light. So we will be incorporating quantum optics into these interferometers in the future. And that's something that we're, if you come over to the labs in NW22, you can see how that's happening.
And that's referring to slide 12, if we just want to put them up for anyone wanting to be reminded of light blue versus dark blue curves.
I have a question. So can this discovery tell us anything about the speed of gravitational waves?
Yes. Eric, I want
to... I guess you can assume that they don't travel with the speed of light. They are massive particles, and that will lead to dispersion. And something that LIGO can measure exquisitely well is the phase of evolution. And that phase of evolution would have been different and that's what we can constrain, what can be that mass of the, for a massive graviton. And this is at the level of 10 to the minus 22 electron volts.
Can we have slide 15, please? We anticipate all your questions, you see.
We try.
So you can see the Compton wavelength being greater than 10 to the 13 kilometers.
I think this means that we saw no dispersion, no evidence of dispersion in the waveform. And that indicates no mass for the graviton. But this is the best limit we could set given the measurement.
Jolyon Bloomfield with MIT. That is an absolutely beautiful plot for modified gravity people like myself. I have another modified gravity question though. Did you search for any evidence of non-GR polarization states?
We searched, but there's not much you can do with only 2 detectors. Yeah. So in order to constrain, let's say, additional polarizations, either longitudinals or scalar, you're going to need more detectors. And this is where the next step is going to be essential for gravitational astronomy, namely adding the 3rd detector, or 4th detector is going to, it's basically a linear problem. You have a number of unknowns. You need those numbers of equations in order to resolve and solve them. So we cannot say anything about additional polarizations.
I can add a little piece to that, which is that the LIGO detectors were actually built for detection. And what that means is they were co-aligned. So they're kind of made to measure the same polarization. And that makes it hard for us to make statements about the other polarization.
Now that we have detections, if we could, we would twist one over, but
just make another one.
But that's hard to do. You did?
So my question is, you're talking about the birth of a new kind of looking, and I'm wondering, I know you guys probably don't love to speculate, but I'd love to know, like when you think about 10 years, 20 years, and beyond, what you think, what you imagine from this.
Yeah, so I think 10 and 20 years is actually, there are some things that we can be quite sure we'll see. And so we'll see neutron stars, we'll see more black holes, families of black holes and neutron stars. We might be able to see some supernovae, some of the things Kip talked about, like cosmic strings. And the thing that I think none of us really dare speculate on, but we dream about, is the things we don't know about. So there's going to be a moment in time when we'll see some blip in our data that we can't say, oh yeah, that's a supernova or that's a neutron star, and then it's going to be, well, what is it? And I think that's the part that is the real unknown in that 10, 20-year time frame. So I think otherwise the sources we think about, we think they're there, and we should just see them. We should see dimmer ones, farther away ones, but then there's this whole unknown piece of it. And you guys have your own opinion on this, I'm sure.
Well, I think one way of assessing what's going to be happening is if you, let's say, consider seeing the cosmos with light being like playing the movie of the universe. This is going to be the end of the silent movie era in astronomy, because you have just added sound. And so I think there's going to be a revolution. There's going to be a revolution. And this is probably maybe not at the pure ZR thing. I mean, clearly we see that things are working so beautifully, but it's going to be in the astrophysics of what you can do once you take those sounds and images and put them together. And you're going to do the astrophysics of the sources in an unprecedented way. And so this is where I think it's going to be the next big thing in the astrophysics of the sources.
Yeah, I think that the analogy to hearing for these detectors is a very useful one, because that's really how we think of these signals, and you can actually listen to them on speakers. So with that analogy, I would say that this event that we're talking about is kind of the loudest thing we could imagine nature producing. It's as if we just got some hearing aids that are only starting to work. And as you lower the noise or increase the sensitivity of the detector, you can reveal more and more things. This is probably the biggest thing you could get, which means you're just starting to hear.
Marsh?
What will it take to build up the potential to searching for the gravitational wave background.
So the question was, what will it take to build up to the potential of searching for the gravitational wave background? So this is the primordial background from the very early universe. And for me personally, I'll answer that is the prize. And I think our detectors and any detectors we can conceive of designing with technologies that are achievable in the next, decade or two are still going to be a ways away from that. But we have some ideas for maybe cutting into a small piece of that signal, but I don't think we're going to see the full-fledged cosmological background. Of 6 orders of magnitude?
Yeah, I mean, if you're looking for the cosmic background at the kind of frequencies you can measure with ground-based detectors, then yeah, we're many orders of magnitude away from what we would expect from the simplest sort of slow roll inflation models. So we operate in the audio band, so 10 hertz to 10 kilohertz, and we expect it from, again, the simplest models of inflation, white spectrum are in that region, which is many orders of magnitude below our sensitivity. Mm-hmm. So probably better off using lower frequency detectors.
However, having said that, if we look at the kind of sources, source that we detected, and you ask how many of them further out we're not detecting at an individual basis, that is going to create something that's going to look like a random noise, stochastic signal. And actually, something that you can entertain here is taking the rate of events you have observed, assuming that this is going to go out to levels where distances where we do not see individual events. You can calculate what is going to be that signature in LIGO. And we've actually done that, and we estimate that even with advanced LIGO as is, that incoherent, if you will, sum of sources that we cannot resolve individually would set a background noise that we should be able to detect, and maybe at the 2 sigma level. Clearly, the more sensitive the detector, the longer you integrate, the more ability you're going to have. This is at the level, though, even well above the signal from our cosmic birth.
Mm-hmm. Yeah, good.
The integration would just be too long right now.
Yeah.
Yes.
So what cooling methods have been implemented to reduce the thermal noise of the system?
Should I take this one?
If you want to, yeah.
You asked about the coatings used on the optics to reduce the thermal noise, is that correct? Yeah, so it turns out that this is one of those things I didn't expect to be talking about today, because it's an interesting technical detail. I've heard someone say, I think this is probably right, that coatings for LIGO are like dust for astronomers. It's one of those things that you don't really want to talk about, but somehow it determines how well things operate. So the current optical coatings are sort of the best we can get for optics, but they're ion beam sputtered coatings. And they're excellent coatings from an optical point of view. We care also about the thermal noise, as you're asking about, so the mechanical properties. And here at MIT, we're working on an experiment to measure this thermal noise for coatings in a way that lets us develop better coatings for future detectors.
You also like do special things to reduce the thermal fluctuation on the mirrors.
So it's another good point that our ability to detect things, once we've eliminated all of the vibrations coming from the ground as best we can, we're left with a limit that's determined just by the motion of the molecules in our mirrors and coatings and in the suspensions. And this is because we're not operating in absolute zero temperature. So we can reduce that noise in our detectors, so make them more sensitive, by picking very high quality materials. And one of the big advances that I alluded to earlier that makes advanced LIGO possible is the very high quality optics we're using. And that you can quantify that in terms of the Q factor of these, or what's the mechanical loss factor. So it turns out the thermal noise from the optics is significantly lower than the thermal noise from the coatings that we put on it. And that's because the coatings are selected for their optical properties.
Bruno.
Nothing. The question comes from PISA. As you know, in PISA there is the Virgo detector. So they asked me questions about your connection. It was mentioned between this event and the emission of high-energy neutrinos.
Do you want to say anything about that?
It comes from PISA, not from me.
It comes from PISA. We have an ongoing coincident analysis with high-energy neutrinos from as detected with the big detectors like IceCube, and we've looked for any correlation of those high-energy neutrinos as they recorded by the instrument, and whether they fall within the error area of our reconstruction of the event, and there is none. And of course, here the hypothesis is that the central ends in, well, of course, after the fact, knowing that these are black holes, there's not much room either for an electromagnetic signature or for a neutrino signature necessarily. But as many things are being carried out quasi in real time, namely in real time, we have almost in real time, we have sent that trigger out to astronomical observatories. There could have been scenario where there is accretion, where there are a situation where we could have high energy neutrino emission, and we have not seen any such correlation.
Claude.
The event seems so significant. I'm wondering, I couldn't tell from your sensitivity curves, where would this have, how would this have appeared if it had occurred during the initial LIGO?
Yeah, we actually have that answer for you on slide 12. Slide 12, please. Yeah, so actually you can see on that rightmost upper plot, so the green curve there is the sensitivity to this type of source at during S6. And the red curve is what it was during observing run 1, and the dot shows you the event. And the reason why the event doesn't lie exactly on the red curve is that those curves are generated for if this binary were optimally oriented. So it's really face on, so that you see the maximum radiation from it, whereas that one wasn't quite. So that's the sensitivity we would expect for a 30 solar mass binary black hole at each of those stages. And you can see that it actually missed the previous previous best. So I think people may be too wowed to ask any more questions. It's all in the papers. So thank you to Matt and to Eric and to everyone for coming, and LIGO group. Well done.
How hungry are you?